Hi everyone, welcome to this new lesson. Today we're going to be talking about volumes. Now there are a few volumes that we've already dealt with back from a geometry standpoint, and we're going to elaborate a little bit more with those volumes in this section. And two of the volumes that stand out, one of them is the volume of a cylinder, and this is going to be for a right circular cylinder. That if we have a circular cylinder as such, then we know how to find its height. We will be able to identify what is its radius, and given the height, then we're going to be able to find its volume. And the same thing is going to go for a rectangular box. If we're given a rectangular box, we can then go through and we can find its volume. And what I'm doing on screen here is just drawing the figures. There we are. And so if we're given, if we're given the length, the width, and then the height, so let's say length, width, and then height of this rectangular box, then we are able to find the volume for that rectangular box. Same thing for the cylinder. So long as we're given the radius and the height, then we're going to be able to find that volume for the cylinder. Now, the nice part about this is that I want you to identify that when we're looking at the cylinder, if we strictly focus on a certain portion of that cylinder, like I will highlight here, where we have this pi r squared, this pi r squared references the area, excuse me about that. This references the area, and more importantly, it references the area of a circle. Now, if you focus on the volume of the rectangular box, we have the length times the width. Well, length times width, you can interpret that as base times height, where this will then interpret the area of a rectangular piece, whereas the area of a circle will be pi r squared. And this is no mistake, simply because we can identify what is known as a cross section. If we identify a cross section in this cylindrical figure, then the area of that cross section is going to be produced by pi r squared. And what the formula for the volume is telling us is that if we take a single cross section and we find its area, so long as we elongate that area along a particular height, then we're going to be able to find the volume, so long as the area doesn't change, right? And that's where these geometric figures get their concepts from. And so what we can do for the rectangular box is we can do the exact same thing. We can find this cross section, and then that cross section will have a certain area amount. We then elongate that area, that length times width, I use this as a height times width, but let's reorient and let's actually get length times width here. That way we can focus on the area that I was referencing. There we are. So we can do length times width, and since it's a rectangular box, it's actually quite nice. There we are. And so this is a rectangular area that we're focusing on that is given by the length times the width. And so for each of these cross sections, we're able to find the area, and that's what the area is actually looking at here. And then all we're doing is we're finding, well, what is that height? And in this particular section, we're going to be working with something very similar. However, we're now going to be using these functions to produce these heights, to produce these areas that we're going to be observing. So, for example, take this function f of x that I have here on screen. I have an x and y axis, and I have a function f of x. Now, assume that I'm going to bound my function f of x between two values. Suppose that we bound it between the bound of a, so I'm going to go with an a bound, and also a b bound. So here we are bounding it between a and b. Now, what we're also going to do is we're going to take this function and we're going to revolve this function about the x-axis. In other words, we're going to rotate this function around the x-axis. And as we rotate this function around the x-axis, what's going to be created is going to be this figure that has a volume. And it's going to be our job to figure out what the volume is. So let's go ahead and work on this rotation here. Okay, so this value is going to come rotated right down here. This value way up here is going to come rotated outward this way. So this function now is being rotated and it looks like this now. It sort of looks like a vase or a vase, however you want to call that. And so this is what we're looking at here, and we want to try to find that volume. So the volume is inside of this figure. And again, this is a three-dimensional figure because we rotated this about the x-axis, therefore creating this three-dimensional figure. And when we say we rotate about a certain axis, we mean we're going to create that three-dimensional figure, and you're going to use 360 degrees to rotate that particular object or that particular curve around a specific axis. And so back to the talk that we were looking at the very top of your screen when we were talking about the volume of a rectangular box or the volume of a cylinder. We know that we can identify a cross-section. So what I want to do here is I want to identify a cross-section. And so in order to identify a cross-section, I'm just going to identify some random value here inside of the interval from A to B. Guess what I'm going to call that? X sub I star. Now, when I find this cross-section, I want to do the exact same thing that we were doing back in the start of chapter 4. I want to take my interval from A to B and I want to subdivide that interval into n subintervals, meaning that we're going to have this delta x value. And so when we're looking at the subdivision of the interval from A to B, we're going to identify this random sample point inside of that interval. And inside of that interval, we get some delta x. So this is your x sub I minus 1, and this is your x sub I. That sample point is right in between there. And that's going to create your interval for delta x. Now, what's nice about this then, if we have these rectangles, that when we have this rectangles, what we will be creating here is going to be this type of figure here. This sort of hockey puck figure. And this figure has a delta x width, so this has a delta x width, and more importantly, we're going to be able to find an area for this given figure. Well, the area here is going to be denoted by the area of this circular face. So how do we find the area of that circular face? Well, let's bring this out. And we're going to say that the area of the cross section is going to be A is equal to pi r squared. But the big question is, what is r? What is the radius for this circular face or for this circular cross section? Well, the radius comes from the center, which is the x-axis, out to the outer part or the outer portion of that circle, where the outer portion here is going to be the function f of x. Therefore, when we want to find the area of that cross section, all we need to do is take pi times the radius squared, but the radius is the function that we're rotating. So we're looking at this. Now that's really interesting, because now this area of the cross section becomes dependent on this function, and more importantly, it becomes dependent on the x value that we choose, that sample point. Therefore, we can rewrite the area of the cross section as your area that's based upon your sample point in those x values. All right, so let's keep going with that. So if we then want to find what is the volume of that small cross-section, because remember, the area of the cross-section is only the area of that face. But if we want to find the volume of the cross-section, because we're creating that small hockey puck, then finding the volume of that cross-sectional area that volume will be equal to the area of the cross-section that we looked at, the x sub I star, multiplied by the height of that cylindrical figure, which will be delta x. And so this is a way to find what is going to be the volume of each individual cross-section that we take. And this is using cylinders. Well, at the end of the day, we really want to find out what is the volume for the whole figure that is made by f of x and the bounds from a to b and the rotation along the x-axis. Well, in order to find that, we need to keep doing the exact same thing that we did here. We need to keep subdividing the interval from a to b into n subintervals, and we'll get a better picture for that volume. So the volume of the figure in question here, well, this is going to be that the volume is going to be approximated if we take all of these smaller cross-sectional volumes and we add them all up for these n subintervals. However, we're not really looking for an approximation once again. Even though approximations are nice, we're not looking for approximations. We want an exact number or an exact process. Therefore, if we want to find that exact process or that exact volume, we then take the limit as n tends to infinity for all of these sub-intervals that we're dividing. But this limit for this summation looks very similar to the Riemann sum definition. And in fact, it really is the exact same Riemann sum definition. Therefore, when we're looking at the volume of a figure that's being rotated along a certain axis, call this the x-axis, for this function that's bounded between a and b, then we can just write that as the integral from a to b for the area of the cross-section we're going to integrate with respect to dx. Now, let's write this up just a little bit more thoroughly. That way we can work with this definition a little bit more. All right, so here's the definition that we're working with. This says that let S be a solid that lies between x is equal to a and x is equal to b. If the cross-sectional area of S in the plane P sub x through x and perpendicular to the x-axis is a of x, where a is a continuous function, then the volume of S is going to be represented by this Riemann sum definition, or we can say it's going to be represented by the integral from a to b for the area of the cross-section, the area of the circular face for that cross-section, a of x, with respect to dx. And remember, dx is going to be that changing width for these smaller puck size cross-sections that we're going to be adding up continuously. And so we now want to use this type of definition to go forth and evaluate these type of integrals that we're going to be observing. So let's jump into some examples. All right, so here's a question at hand that we want to find the volume of the solid obtained by rotating the region bounded by the function f of x, which is given by 4x minus x squared, and the x-axis, and we're going to rotate this about the x-axis. So the first thing that we want to do, again, is we want to sketch this region. So that's what I'm going to do really quickly, is I'm just going to get a quick scale going for my axes here before we start sketching it. So here's y and then here's x. So looking at the graph, f of x is equal to 4x minus x squared. So this tells me that I'm looking at a parabola. It's opening downward, and the parabola is not being vertically compressed or vertically stretched, because there is no other constant besides -1 multiplying the x squared value, which means that I got to find its vertex. So to find its vertex, I'm going to use the vertex formula. So the vertex formula says that for the x component, you take -b over 2a, and for the y component, you evaluate -b over 2a into the function that you're working with. So if I want my vertex, I'm going to take my x value, and this is going to be -b over 2a. So negative my b quantity is 4, divided by 2a, a is -1. So this gets me +2. And then in order to find the vertex, I'm going to evaluate 2 into my function. So this is 4 times 2 minus 2 squared. All right, so 4 times 2, that's 8, minus 2 squared, which is 4. So 8 minus 4 gets us 4. So there's my vertex. The vertex then occurs at 2, 4. Okay, so I at least have some point of reference as to how high this parabola is going to go. Now what I want to do is I want to find my x-intercepts. So in order to find my x-intercepts, I'm going to go ahead and I'm going to set my function equal to 0. In doing so, I can factor out an x, and therefore I get two different x values, x is equal to 0 or x is equal to 4. So x is equal to 0 or x is equal to 4 for these x-intercepts. So ordered pairwise, this gets me 0, 0, and this gets me 4, 0. So this now tells me almost everything that I need to know about this parabola. I have these x-intercepts, and I also have the vertex. Therefore, I can now start creating the scale that I wanted to from the very beginning. So I know that my y-coordinates, the highest amount, they're going to go up to 4. And there we are. 1, 2, 3, and 4. Now, my x values are going to go all the way out to 4 as well. There we are. So let's condense this down just a little bit more. There we go. So my function here, again, we're at 2. I'm up all the way up at 4, 0, 0, and then 4, 0, like this. So here's my parabola. There we are. And so again, this is my function f of x, which is 4x minus x squared. And so the area that is being bounded here, or the region that is being bounded, is, as they state in the prompt, the bounded region by f of x and the x-axis. Therefore, the region that we are focusing on here is going to be this region right in here. And so now we're going to take this region and we're going to start rotating this region about the x-axis. And so what I'm going to do here is I'm just going to create a different sketch. That way I can annotate that sketch without annotating or without making it look too convoluted once I get to that rotation and start analyzing that three-dimensional figure. All right, so let me go through and let me sketch this other figure. Now again, the rotation of this figure, I'm going to try to keep a scale on here for the figure. But again, as I'm rotating this figure, remember, we're rotating here and we're trying to make the rotation look like a three-dimensional rotation. So this region, oops, for this parabola will then be rotated about the x-axis. So again, notice you're going to see me put this rotation symbol on whatever axis we're rotating about. And therefore, we now create these figures here. So this kind of looks like a, in my mind, it kind of looks like a Christmas ornament. So we've created this three-dimensional figure now, and we want to find its volume. So if we want to find the volume, then naturally we just need to find what is the area of one of the cross-sections. And remember, the area of the cross-section, or the cross-section that you're going to be looking at, that cross-section needs to be perpendicular to your x-axis, or in this case, needs to be perpendicular to the axis of rotation. So that's what we're going to focus on here when we want to find this area of the cross-section. So I'm just going to identify a random cross-section in my figure. And coincidentally, I'm just going to go after this figure right here. All right, so I need to find that area of this figure. Now, the area of that figure, whatever x sub I, whatever interval I choose here, or whatever sample point I choose here, notice that that's going to have a direct correlation to whatever figure or whatever sample point I choose. That sample point will then create a radius, and this is why I create these two figures, is so that I could then analyze what is that radius. So in order to find the radius here, or let's say to find the area of this cross-section, the area of the cross-section is going to be pi r squared. Now again, the radius is going to be this radius that we're looking at. So the bottom point is y is equal to 0. The top point is f of x. In other words, y is equal to 4x minus x squared. Therefore, my radius is just 4x minus x squared for all of these individual sample points cross-sectional areas. So any area or any sample point that we choose inside of that interval from 0 to 4 will have a different height representation for that radius, but that height representation is given by this function f of x. So all we need to do now is we just need to integrate the area of this cross-section. So to complete this, we're going to say that the volume is going to be the integral, and we're going to go from the x value of 0 all the way to the x value of 4. That's where our sample points are going to lie in, from 0 to 4. We're going to integrate the area that we found, and that's integrating pi times 4x minus x squared, quantity squared, and then we need to give the volume here, so we need that dx. So we're going to multiply, or in other words, we're going to integrate with respect to dx. All right, so let's integrate this with respect to dx. Oops, sorry about that. All right, here we go. Now, pi is a constant, so it factors straight through the integral, multiplied by the integral from 0 to 4. I'm going to expand this binomial. Expanding this binomial, 4x squared, so that's going to be 16x squared. There's going to be a minus 2 times 4x times x squared. So that's going to be 8x cubed plus the last term squared. So that's going to be plus x to the power of 4 with respect to dx. Now we can take term by term and we can integrate. So taking this term by term and integrating, we're going to get 16 divided by 3 times x to the power of 3 minus 2 times x to the 4th plus 1/5 times x to the power of 5. And this is going to be from 0 to 4. All we have to do now is evaluate. Pi multiplied by 16 divided by 3 times 4 cubed minus 2 times 4 to the power of 4 plus 1/5 times 4 to the power of 5. Now, looking at every individual term has a value of x. So if I evaluate my value of x is equal to 0 onto this function, then everything is going to cancel out, at least for those terms. So I'm just going to bypass that part and just say that we are only evaluating the function here, or this antiderivative, at 4, because the rest of the values will then cancel. So 4 to the power of 3 should get us 64. So 64 times 16 is going to get us 1024, now divided by 3. I have 4 to the power of 4, which gets us 256, and that's going to be multiplying 2, which is 512. But then I have a denominator of 3, so I'll come back to that. So this is minus 512 plus 4 to the power of 5 gets us 1024, and that's going to be divided by 5. So we have 1024 divided by 3 minus 512 plus 1024 divided by 5. So our overall answer will then be 512 divided by 15 multiplied by pi. In other words, this is 512 pi all divided by 15. And again, since this is going to be a volume, this is going to be some type of cubed units or cubic units. Right, for whatever volume we find here. So again, it's going to be important for us to be able to not only sketch the figure, but to go through the whole process and identify what is going to be the radius that we're working with. Once we identify what that radius is, we could then identify what is the area of the face of that cross section and then integrate over the interval where those cross sections are going to be spanning. So let's try a different problem now. Let obtained by rotating the region that's bounded by 2x is equal to y squared, x is equal to 0, y is equal to 0, and rotated about the y-axis. So again, the first thing that we're going to do is we're going to graph the functions that we're given. The first function that I'm given here is 2x is equal to y squared. So 2x is equal to y squared. That can also be rewritten as x is equal to 1/2 y squared. So if x is 0, then y is going to be 0 as well. This time I'm going to take y values. So if, let's say, y is 2, so then 2 squared is 4. 4 divided by 2 is just 2. So when y is equal to 2, we get 2 for the x value. When y is equal to 4, that's going to get me 16. 16 divided by 2 is going to be 8. So when the y value is 4, the x value is going to be 8. And again, this holds true for a negative y values as well. And so this function here, sorry, not this function, this equation represents 2x is equal to y squared. Now we're also bounding by x is equal to 0 and y is equal to 4. So let's identify x is equal to 0. X is equal to 0 is going to be another name for the y-axis. So again, this is x is equal to 0. And we also have y is equal to 4. So when we're doing y is equal to 4, right, so y is equal to 4, well, if y is equal to 4, then that produces an x value of 8. So nonetheless, we get y is equal to 4 here. And so we want to focus on the area that's bounded by these three curves. That area, or that region that's bounded by these three curves, is this region right in here. And that's the region that is then going to be rotated about the y-axis. So again, I don't want to rotate this region automatically just right here with this particular figure. What I want to do is I want to create another figure. That way that figure won't have to be doesn't have to be as convoluted as this figure will be if we use this as a rotation about the y-axis. So let's go ahead and let's sketch that rotation about the y-axis here on this other figure. Alright, so here's my axis. The one that I'm going to be revolving here is going to be around the y-axis. And so again, this figure has a parabola here. As such, and then rotating about the y-axis will then create this circular figure at the top, and therefore it's going to create these circular portions here as well. So this is the volume that we're trying to find. Now, in trying to find this volume, we need to identify a cross-section. But here, the cross-sections are going to be perpendicular to the y-axis. Therefore, the integration that needs to take place here will be the integration with respect to the y-axis. So when we want to look at a cross-section here, again, we'll take a cross-section. There we are. And we need to find the area of this cross-section. So the first thing that we're going to need to find is what is the radius. Now, finding the radius, we always go back to the initial picture. If we're picking a sample point inside of the y values, then that radius will be extending from the y-axis, in other words, x is equal to 0, all the way out to this point here, which is this equation of this parabola, which is x is equal to 1/2 y squared. And again, this is your radius. So again, that's the same radius r. So if we want to find the area for that cross-section, this is going to be an area in terms of y, and we're going to take pi r squared, and again, r in this case is x is equal to 1/2 y squared. So this is our area function in terms of y. And we could simplify this a little bit more. 1/2 squared is 1/4. Y squared squared, that's y to the 4th. So this turns into pi over 4 y to the 4th. And that's a function that we're integrating. So again, we're going to do this with respect to the y-axis. So integrating with respect to the y-axis, then our y bounds for that initial region are from 0 to 4. We're going to integrate the function that we found, which is pi over 4, y to the power of 4, and we're doing this with respect to dy. And so, once again, pi fourths, that is a constant, so it moves straight through the integral. Y to the 4th integrated becomes, the integral of y to the 4th is what we're left with, dy. And when we integrate y to the 4th, we're left with 1/5 y to the 5th evaluated from 0 to 4. And so once again, this is pi fourths multiplied by 1/5 multiplied by 4 to the power of 5. And again, we could evaluate the function at 0, but evaluating the function at 0 will cancel that whole term out. And so here we get 4 to the 5th, but 4 to the 5th is being divided by a single 4. That means that's going to be 4 to the power of 4. So 4 to the power of 4 gets us 256. So we get 256 pi divided by 5. And again, this is some cubic units, because it's a volume that we're finding. So again, we always have to pay attention to what is the radius and how are we initially identifying that radius. We can integrate with respect to the x-axis or with respect to the y-axis, whichever one we see fit and whichever one will help us evaluate that particular volume the easiest. Now let's try another example, and this example will be a little bit more different, but it's going to be different in a good type of way. So here's the question that we're looking at. This says to find the volume of the solid obtained by rotating the region bounded by y is equal to x cubed, y is equal to 0, and x is equal to 2 about the y-axis. So let's go ahead and let's again sketch the area first. Once we sketch the area that's being bounded, then we can go through and we can talk about the rotation of that particular area about the given axis. Alright, so here is your x-axis, here is your y-axis. Let's give this a good scale now. Okay, so we have y is equal to x cubed. Y is equal to x cubed, that's again your cubic function, so if x is 1, then y is 1. And if x is 2, then y is 8. And if x is 0, then y is 0 as well. Alright, so here we are, we have y is equal to x cubed, and we're also going to have y is equal to 0. Y is equal to 0 is another name for your x-axis. So here's y is equal to 0, and we're going to have x is equal to 2. And so again, what we want to do is we want to find this region that is bounded by the curves that are given to us. So the region that is bounded by the curves that are given to us is this region right in here. That's a region that we're going to be rotating about the y-axis. So let's go ahead and let's take some time and let's start rotating that region about the y-axis. So again, I'm just going to go through on this right-hand side, and I'm going to recreate my picture. But now I'm going to recreate my picture using that rotation that we want to see about the y-axis. So naturally, I'm going to use my x-axis a little bit longer in both directions. So here's x, here's y. All right, there's 1 and 2. Alright, so let's give this a shot. So I know the region intersects at 2 and 8 and -2, -8. Alright, we're going to make a circular rotation about this y-axis. So again, we're rotating about the y-axis. Alright, therefore we're creating this type of figure. Now, notice the area that's being rotated. The area that's being rotated covers all the way down to the x-axis. Therefore, all of these lines are going to come straight down. There we are. And this bottom part is also going to create that rotation. There we are. But now the inside of this figure is where we have that volume that we're trying to find. It's not the volume of this cylinder, but it's a volume that's bounded inside of that cylinder. And that volume that is bounded inside of this cylinder is made by x cubed. Oops. So when we want to look at the cross section for this particular area, we're going to have to be very, very careful here, because the cross section for this area, not only does it create this circular figure, the circular cross section, but the circular cross section for that area has an embedded hole right smack in the middle. Therefore, the area that we're trying to find is the area made by this little disc, or as we call it, that washer. So this is your cross section. It looks like a washer. And these washers are the things that you use for when you're screwing something on. Maybe you're tightening a bolt or using nuts and bolts to tighten something up. You'll typically put a washer in between the bolt and the surface. That way your bolt could then clamp onto that surface. So this is what we are then trying to find for that area. So in order to find the area of this cross section, I am going to extract this washer. So extracting this washer, I'm going to give you a frontal view of this washer. The frontal view of this washer is just going to be a circle with that hole in the middle. And again, the area that we're trying to find is this area right here. So this makes a certain radius, and we have to find what radii that is. So let's use some of our algebraic techniques here. So the first thing that I want to do is I want to identify that I do have some center here, and that center is this y-axis. And I'm going to measure the radius from that y-axis. And you're going to see that I have two different radii. The first radius that I have is going to be this radius right in here that will be measured from the y-axis to the innermost circle of that washer. So that first radius is right in here, and I need to find out what that radius is. And again, taking any sample point here, that's going to be my first radius. So I'm going to call this radius of the inner, because it's an inner radius as we see here. So this is radius inner. Alright, and I'm going to say this is radius inner. So in order to find that radius, I am going to now consider this function that is making that radius. Well, it goes out to y is equal to x cubed. So if it goes out to y is equal to x cubed, let's go through and let's figure out what is that value then. Since this cross section will be perpendicular to this y-axis, then I'm going to be integrating with respect to y because that's where all of my sample points are going to lie in. So I need to solve for x in this particular instance for that green function. So that function, x cubed is equal to y, I'm going to solve for x by taking the cube root of both sides. In doing so, I get that x is equal to the cube root of y. And that is my innermost radius here. My innermost radius, that r inner, is going to be equal to the cube root of y. That's the innermost radius. Now let's talk about the outermost radius. So if we're looking at the outermost radius is going to be the radius made by the y-axis measured out to the outermost region of that washer. So the outermost region of that washer, that's going to be the next radius that I'm looking for. And that's going to be the outer radius. So that outer radius is then measured again from the y-axis out to that specific value. Again, if we're measuring distances in terms of x, then this is going to be from x is equal to 0 all the way out to x is equal to 2. Therefore, the outer radius is going to be a radii of 2. And that 2 stays constant throughout this whole rotation. It doesn't move. The only one that does change is the inner radius, and that inner radius only changes depending on what sample point we chose on that interval from 0 to 8. If it's closer to 8, then that inner radius is almost as large as the outer radius. If that sample point that we choose is y is equal to, let's say, 1/2, then this inner radius is going to be slightly smaller than this outer radius. So now that we have this, let's go through and let's keep finding what is the area of that cross section. So finding the area of the cross section, we're going to take the difference in between the two. The area made by the outer circle minus the area made by that inner circle. So I'm going to take the area of the outer circle, which is pi, times the outer radius squared, minus pi times the inner circle, the inner radius, that's y to the power of 1/3, quantity squared. Therefore, my area function in terms of y is going to be 4 pi minus y to the power of 2/3 pi. This is the area function. Again, outer area minus the inner area. That way we can extract what is the area of this washer. And so when we want to set up this integral, for my volume, I just need to do the integral for my sample points. Sample points, we're choosing the y-axis, so naturally that area that is initially bounded goes from 0 to 8, and we integrate over the area function. That area function is 4 pi minus y to the power of 2/3 pi dy. And so again, let's break this down just a little bit more. I'll use this here. So this here is the area of the outer circle. And then this here is the area of the innermost circle. And so again, we always go through that, finding the area of the outer minus the area of the inner circles, that we can find the area of that washer. All we have to come over here now and do is integrate. So running through this whole integration, we have pi as a constant. So pi can be factored straight out of the integral, and we have 4 minus y to the power of 2/3 that we then need to integrate with respect to dy. Integrating 4 with respect to y, this gets us 4y minus y to the power of 2/3. We're going to add 1. 2/3 plus 1 gets us 5/3. Since 5/3 is a fraction, we're going to multiply by the reciprocal. And we evaluate this from 0 to 8. Now again, every single term has a y component. Therefore, whenever I insert my 0 into those y components, they're going to cancel out. So I'm only going to evaluate this function for 8. So it's 4 times 8 minus 3/5 multiplied by 8 to the power of 5/3. So let's do some calculations here. 4 times 8, that's going to be 32. Oops, sorry, that's pi multiplied by 32 minus, I'm going to have 3/5, but then 8 to the power of 5/3. Well, since the exponent has a divisor of 3, that's going to be a cube root, so 8 cubed is 2, but then I'm going to take 2 and I'm going to raise that to the power of 5, which makes it 32. So naturally, 8 to the power of 5/3 becomes 32, and then 32 is going to be multiplied by 3, which gets me 96. So we get 96 divided by 5. And now we just perform that operation. 32 minus 96 divided by 5 will then get us 64 divided by 5, but we're multiplying by pi, which means this is 64 pi divided by 5 cubic units. There we are. So this particular method is known as your washer method, whereas the previous two methods were known as your disk method, simply because the area of the cross section is making a disk. And in this particular instance for this problem, the area that was being made was a washer. So again, these two methods are known as the disk and the washer method for finding volumes. Now, let's up the ante just a little bit more, and let's see if we can figure some of these out. All right, we're going to do an example where we are either going to rotate about the x or the y axis, but there's going to be an added catch to this. All right, so let's follow along with this problem. All right, so here's that next question that says that we have to find the volume of the solid obtained by rotating the region bounded by y is equal to x cubed, y is equal to 1, x is equal to 2, and we're going to rotate this about the line y is equal to -3. All right, so there's a lot going on here, and let's go through and start unpacking all of this. All right, so the first thing I'm going to do is I'm going to extend my y-axis down below, because I also need to account for y is equal to -3. Okay, here we go. So y is equal to x cubed. Again, I'm going to go through the same process here. If x is 2, then y naturally has to be 8. All right, there we are. So here is my graph for y is equal to x cubed. And again, it can be proceeding down in that direction. Y is equal to 1. So I'm going to use y is equal to 1. And let's get this going. Where's y is equal to 1? There we are. All right, so we have y is equal to 1. And I also want x is equal to 2. So x is equal to 2 is, again, this equation here. And we should now be able to extract what area we are bounding by these three curves. That area that is being bounded is this area right in here. And that is the region that we're going to rotate, and more importantly, we're going to rotate that region about the axis that is y is equal to -3. So y is equal to -3 axis. Let's go ahead and let's jot that down. -3 right down here. There we are. So this is the axis that we will be rotating along. Y is equal to -3. There we are. So let's go ahead and let's start creating a sketch for this. All right, so I'm going to take all of this, and again, notice that I never want to do the drawings on my specific sketch of the region. And this is because if we do, certain items or certain drawings start getting too convoluted, and what happens then is that you might misinterpret a radius, or you might be able to misinterpret the function itself. So I always encourage everyone to look at the picture that is being rotated differently than the sketch of what you made. So let's go ahead and let's sketch this out. So here's going to be my x-axis. And I'm going to have my y-axis. Oops. There we are. So here's y, then here's x. I'm going to insert my scale here. And same thing down below. All right, I'm also going to find y is equal to -3. And this is because I'm going to be rotating across y is equal to -3. All right, so let's identify that axis of rotation. Right down here. There we are. And again, this is where we are going to be rotating. Now, you're going to see that the figure, that region, stops at x is equal to 1, but then it goes all the way to x is equal to 2. All right, so we're going to make sure we keep that in mind. Now, as we start rotating this figure, I just want to make sure I get certain points. That way I can connect my points with those circular arcs, and then I can go through and sketch the rest of the figure. All right, so let's get the outer one over here, 2 and 8. That one's the easiest one. All right, so here we go. I'm going to have 2 all the way up at 8. All right, my other point is going to be at 1, 1. So at 1, 1, this now creates my outer figure. There we are. Now I need to find out how far this point is from this line and reflect that across. So this point from this line is a total distance of 1, 2, 3, 4. So I'm going to move that distance away from this line as well, from that axis of rotation. So 1, 2, 3, 4. There we are. So this point here, 1, 1, gets reflected downward towards 1, negative 7. All right. I'm going to do the same thing over here. This point is now going to be reflected downward. So if this is 8 measured from the positive x-axis, then it's measured 3 down below. Then that's going to be a total distance of 11. And that's going to be moving downward from this given axis of rotation. So negative 3 minus 11, that should be negative 14. As you can see, I ran out of axes there, and that's completely fine. I just want to make sure we graph this adequately. There we are. And now when we're talking about doing the rotation here, the rotation is now going to take this and revolve it. And I have this circular figure. As such. Now, we got to be careful here because there's another circle that is being embedded here. That other circle is going to be embedded by y is equal to 1. Y is equal to 1 is this bottom bound for this region, and it's also creating this circular portion. All right, so let's go ahead and let's account for that. Kind of like we have this open circle right in there. There we are. So here's the volume that we're looking at for that specific region. Now, finding the volume again is going to be a little bit more difficult, but again, we're up to that task. So the first thing that we're going to do then is we're going to identify that if we have to take a cross section, and we do, then the cross section is going to be perpendicular to the axis of rotation. Therefore, any axis that we find, or any, cross-sectional area that we find, will then need to be perpendicular to the y is equal to negative 3 axis. Therefore, every single sample point is in the x coordinate. All right, very important for us to know. So let's take a random sample point. So if we take a sample point, let's say here, we're going to then generate a circular cross section that has 2 different circles embedded in it. All right, it's hard to see there, and that's why I always extract those cross-sectional areas. This is going to be a washer. So we have an outer circle, then we're going to have an inner circle, and we want to find what is the area of this washer. In order to do that, we need to identify the radii. Notice the radius is always going to be measured from the axis of rotation. So we do have a center here, but the center is no longer the y-axis or the x-axis. The center is now y is equal to negative 3. So we got to keep that in mind. All right, so once we have that, let's go through and let's start identifying what these radii are going to be. So let's go with the innermost radius. The innermost radius, as you can see, it's starting to look way convoluted now. The inner radius is going to be made from y is equal to negative 3 up until that bottom portion of that region. That means that my radius is going to be measured here. So this is the innermost radius. Now we want to find that total distance, that total measurement. So the measurement here, or this distance, is going to be 1 minus -3, which is a total distance of 4. Now, how do we find that out? Well, we just go to the y function and we subtract out the axis of rotation. So 1 minus -3. So this is 1 minus -3, which then becomes just 4. Therefore, the inner radius that we are looking at here once again, we said that that was just going to be 4. The outer radius, let's get that outer radius going. So that outer radius, all right, the outer radius, that one is going to be measured again from the axis of rotation all the way up to that outer portion of that volume. So in order to find this is going to be our outer. We're going to again take top minus the bottom. So the top is y is equal to x cubed. So that's y is equal to x cubed minus the axis of rotation. The axis of rotation is -3, which means my outer radius is x cubed plus 3. So outer radius, we found that to be x cubed plus 3. So again, as you can see, there's a lot of writing going on. And again, if we don't produce two different drawings, then one of the drawings is going to get really convoluted. And again, it gets really hard to see what's what. So think about this from a grading standpoint. If I cannot see what your thought process is, then chances are I cannot award partial credit. So please be very mindful of that. So the area of this cross section is going to be the area of the outer circle. So the area of the outer circle, we said the outer radius is x cubed plus 3. So this is pi r squared minus pi, and this is going to be pi r squared from the inner as such. Therefore, when we want to find the volume of the figure, again, the sample points are in the x-axis, and this region that is initially bounded goes from x is equal to 1 to x is equal to 2. We integrate this formula for my area, which is pi times x cubed plus 3 quantities squared minus 16 pi, and this is going to be dx. So what does that mean for us then? Well, the pi is a constant. That's going to factor out. We go from the integral from 1 to 2. Let's expand this. X cubed squared, that's x to the 6. 2 times x cubed times 3, that's going to be 6x cubed plus 3 squared, which is 9, minus 16. This is all dx. Which means this integral is, this volume is pi times the integral from 1 to 2. And this is going to be for x to the 6 plus 6x cubed minus 7. All right, so, dx. All we do is integrate. And when we integrate this, and again, you can integrate this on your own, but after a while that you integrate, you will get 471 pi divided by 14. And again, this is cubic units. Now, for these types of questions, what I'm expecting on the homework and on the exam is going to be for you to be able to replicate what is that region that is being rotated. Next, can you identify the solid that's being rotated? Next, can you identify what is the area function that we're working with? And then finally, can you then find the volume? Meaning, can you integrate that area function that you found? That's what I'm looking for in this section. All right, if you go through and if you just tell me that the volume is going to be this volume here, and then you go through and solve that, there's going to be a lot of questions that I have. All right, so please be very mindful of that. All right, but this is how to find volume using the disk and the washer method. So I hope that you all enjoyed this lesson, and stick around and we'll come back for another volume lesson, but this time using what is known as cylindrical shells. Till next time, please stay safe.